Good afternoon, everyone.
An MRI like I've got. Yeah.
Welcome to the first faculty seminar of 2020. We all have a vision for 2020, I'm assuming. You're gonna get sick of that acronym or that term. It gives me great pleasure to introduce our speaker today, but first I'll introduce myself. My name is Jim House. I'm head of the Department of Food and Human Nutritional Sciences, and it gives me great pleasure to introduce Dr. Carla Taylor. Dr. Taylor is a professor in the Department of Food and Human Nutritional Sciences. He's also team leader and principal scientist at the Canadian Centre for Agri-Food Research in Health and Medicine, shortened to CCARM, so you can use CCARM, that makes life a little easier. Dr. Taylor is a Manitoba girl. She was born in Oak Lake. Anybody know where Oak Lake is? I knew Martin would know where Oak Lake is. Born in Oak Lake, did her undergraduate work here at the University of Manitoba and graduated from what was then the Faculty of Human Ecology in the Department of Foods and Nutrition. Did a PhD at the University of Guelph and postdocs at Michigan and University of Washington in Seattle. Dr. Taylor has been with the department and teaching in areas related to macronutrients, metabolism, has a long interest in looking at the role of nutrition in diabetes and cardiovascular disease, and has won a number of awards in relation to the research and also for her teaching activities. As an example of some of the research awards, she was awarded the International Life Sciences Institute Award for her work in nutrition, and was also awarded the Centrum Foundation New Scientist Award in 2005 from the Canadian Society of Nutritional Sciences, now the Canadian Nutrition Society. Dr. Taylor has been doing some really interesting work and has positioned this beautiful title on pulses for your pulse and fats for your fat. I know we're looking forward to hearing a lot of the research that's going on in Dr. Taylor's lab, so would you please join with me in welcoming Carla to the podium.
Great, thank you very much, Jim. And it's a pleasure to be here this afternoon and to be presenting to the faculty. And just going to give you a little bit of an outline for today's presentation. I'm going to obviously be talking about two examples of research, pulses and dietary fats. And I'm going to do this through kind of a series of questions, so you kind of can see how one thing led to another, to where some of our current questions are. And so I think for any of us that have been involved in science for a while, we see that it's kind of a journey, and sometimes it's not a very straight road, but things kind of get to a certain point. I'll be showing you various models and tools that we use. You'll certainly see that I'm involved in very multidisciplinary team-based approaches. Certainly when I talk about what's being done, it's we, it's not me, and there's certainly many trainees, technicians, collaborators, my co-investigator Peter Zraka have all been very important to the work I'm going to show today, and I've selected some things to highlight. Some of the things I might be going over just the highlights, and if you want to know more about a particular study, ask me in the question part. And as you're sitting there, I'm going to challenge all of you to kind of think about the work I'm doing from a nutrition perspective with agri-foods, and how is that being influenced by plant breeding? How is it influenced by genotype times environment interactions and things that we might not be aware of? How is it influenced by food science and food technology? Or how we study animal metabolism, use, say, rodent models to understand human nutrition. So kind of think about the examples I'm presenting and think about, how this fits together within the faculty, and as nutrition now being part of this faculty, how can we build on this, all of our expertise to address these various questions about food and improving our health. So going to start off with an easy question. I think most people in this room can appreciate that pulses stand for dried beans, peas, lentils, and chickpeas. Canada's very good at producing them and exporting them. We're probably less good at actually consuming them. And the other type of pulse that was in my title refers to the pulse when the heart is pumping our blood, right? So the pulse that you can feel when you put your fingers on your wrist. And depending on whether the blood vessels are stiff or elastic, that's going to change the velocity of the blood flowing through those vessels, and it's also going to change the shape of the pulse waveform. Okay, so you can see there when the vessel is stiff how that pulse is moving quite quickly. Because in a sense, instead of having a nice elastic vessel, we have a vessel that's operating more like a stiff pipe. So then, what makes blood vessels stiff? Okay, so you may have heard of the term atherosclerosis. So when we get these buildup of lipid-based deposits in the blood vessels, it leads to both a hardening and a narrowing of the vessels, and they lose elasticity. What is the time frame for these changes to happen in the blood vessel? And so you can see here, I have a pictorial starting out with changes that can happen over hours and days to those that are over months and years. Right? So it's really over a lifetime that atherosclerosis is developing in our blood vessels. Okay? And as early as in 20s and maybe even in the teens, there can be the early stages of atherosclerosis detected. How does somebody know if they've got atherosclerosis? And this is kind of one of the big challenges of the whole cardiovascular area, is that cardiovascular disease is basically asymptomatic until someone has a heart attack or a stroke. And as you can see, next to cancer, heart attacks and strokes are the second major cause of death in Canada. Lots of times people talk about blood cholesterol levels, but blood cholesterol levels are really just a risk factor. Okay? They're based on large population studies, and we know that someone can have high cholesterol and not have a heart attack or stroke, and people with low cholesterol can. Right? So we need to have more direct assessments of our blood vessels and to have assessments of that very early stage of disease. Okay. I think we hear a lot about cardiovascular disease in terms of it affecting the heart attacks, the brain, and strokes, but the vessels throughout the body are being affected. And peripheral artery disease is when the cardiovascular disease is in the legs, the narrowing of those blood vessels, reducing blood flow to the legs. And that can make it very difficult for someone to walk even short distances. And the reason I'm bringing up peripheral artery disease is because it's the condition that we decided to use for our very first clinical study with pulses. Okay? The way in which PAD is diagnosed is by the ankle brachial index. So it's getting the blood pressure at the ankle over the arm. And if that ratio is less than 0.9, someone is diagnosed as having PAD. You can see on the left side some of the statistics around PAD. And unfortunately, many people don't know that they have this condition. So for our first study with pulses, which was back when Pulse Canada got an initiative together to say, we need more human trials on pulses. We need to update what's known. And so we posed the question, can pulses improve the blood flow in individuals who have peripheral artery disease? And to do this study, we designed an 8-week study in which individuals participating consumed half a cup daily of either beans, peas, lentils, or chickpeas. So on any given day, they might have a food item with kidney beans, another day, green peas, and so forth. At the beginning and end of the study, we took various assessments, and also we did some work at the beginning to understand how much people were actually consuming pulses, because obviously we didn't want to recruit people who are already consuming a lot of pulses. Now with PAD, this is an older age group, so you can see the average age was 70. And this is a group of individuals who are on medications for various conditions because they have high cholesterol, high blood pressure, diabetes is a common cofactor in this disease as well. And these individuals then participated in our study. When we asked them about their typical consumption of pulses, you can see that 90% of them said that during the past month they had only consumed pulses 1 to 3 times per month. And for many of the individuals, it was less than that. So meaning that it wasn't even once a month, and it could have been rarely or never. The interesting thing is, by providing people with various food items that it was convenient for them to use, by the end of the study, many of them were asking us, how can we get these food items? We'd like to continue eating pulses. Okay. So we had developed a 2-week menu cycle so that we could send people home with 1 item per day that they could heat up and consume along with their usual diet. And very interestingly, we found that over 8 weeks, even in people who have later stages of cardiovascular disease, we were able to improve blood flow to the legs. So the fact that the ABIs increased on both the right and left side shows an improvement. This panel here on the side is plotting baseline and final or end of study for individual participants. And so just eyeballing those lines, all but 5 participants that have the asterisk, everyone else had some sort of improvement in their ABIs. Okay. The improvement happened because of better flow to the, or better blood pressures in the ankle. Okay, it wasn't because of the arm, it was because blood flow to the leg was being improved. In this study, we didn't have a formal assessment of ability to walk a certain distance, because you can do a treadmill test for this, for example. But there were certainly comments from participants that they perceived, at least, that they could walk further without any pain. Okay. We did not find any correlation, though, with the improvement in blood pressures and cholesterol lowering. Okay. We did find that the pulses did lower their blood cholesterol a little bit, even though they were already on medications. But the changes that we're seeing are not connected with the lowering of the cholesterol, which we would typically associate with the fiber component in the pulse foods. And so this has led to us starting to hypothesize that it's the flavonoid compounds, it's the phytochemicals that are in the pulses that are potentially interacting directly with the blood vessel wall. Okay. So that study was an 8-week study, so a chronic study. The next study that I'm going to show you here was done by Jamie Clark as part of her PhD thesis. And this was where we started to ask the question, how quickly can we see changes in the blood vessels after people consume pulses? Okay, so you're probably aware of with, say, glycemic testing, you find out how a person's blood glucose responds to the food that they've just consumed. Here we made it a post-prandial test looking at the effects of different bean types. People came in fasting. We got baseline measurements. They got to eat beans for breakfast, 3/4 cup serving, compared to rice as our comparator food. And then we took the vascular measurements at 2 and 6 hours later. Okay. Okay. So going back to this initial schematic that I showed you, this with the postprandial changes is allowing us to focus on what are these very early changes happening right after we consume a particular food. Okay? And so with this type of study, we can measure something called vascular tone. And this is really about how relaxed or tense are our blood vessels. And some of this knowledge comes from early studies showing that foods can affect our vascular tone. And the early studies being done with this type of postprandial assessment, we're taking something like the McDonald's meal, a burger and French fries, and showing that in the 2 to 3 hours after consuming that type of food, that the blood vessels became more tense. Okay. When we did this with providing people with the different types of beans, we found that black beans and red kidney beans cause the vessels to become more relaxed. Okay? And so now we're wanting to follow up with this and also learn more about what type of flavonoid compounds were maybe absorbed from these beans at each of these different sessions, and can we start linking those with the type of changes that were happening in the blood vessel. Other questions people have come up with from this is maybe we could combine a meal that has pulses with something which is less healthy on our blood vessels and maybe kind of cancel out the effects a bit, right? Maybe we could use pulses to that benefit. Okay. So those were 2 examples of human studies that we've done. And now I'm going to move into some examples of work that we've done in animal models, because we needed a way to start and sort out a little bit faster which pulse type, right? So thinking from our first human study, we fed MITS pulses. Is one or are all of those pulse types beneficial? And also by using a rodent model, we can start dissecting out vessels and start looking to see what type of changes might be happening in those vessels. So this spontaneously hypertensive rat, the SHR, is a model for arterial stiffness. And we provided these rats with diets for 4 weeks. We did the typical overnight soaking and boiling of the pulses, except for the lentils that were just boiled. And because we were incorporating these into a semi-purified rodent diet, we needed to freeze dry these so that we could powder them and incorporate them into the diets. And based on some previous work that was in the literature, a group in Colorado that's been studying pulses for cancer prevention, we did an incorporation of 30% weight per weight into the diet. And so if we were to calculate the amount of energy in this diet from the pulses and compare it to humans, people who are consuming a vegetarian diet, which is heavily based on pulses as their protein source, they would be consuming a similar proportion of calories from pulses. Okay. And then for this first study, we had the different pulses represented. And you can see when we had the bean diet, for example, there was a mixture of 4 different pulses. Okay. This is showing us what happened to the arterial wall thickness of the aorta from these animals. Okay, so we can actually measure what that thickness is. And so on the far left here, where we have the WKY rat, those are the control rats that have a normal blood pressure. And so you can see that they have a less thick arterial wall than the SHR control. Okay? And it's because of the pressure that it's exerted with the high blood pressure. It causes a thickening of the arterial wall. And amongst the different diets that we tested, the SHR group that was fed the lentils had the significant reduction in the arterial wall thickness. And if seeing is believing, here is some sections from this particular study. And so you can see here the thickness of the normal WKY rat versus the SHR, the hypertensive rat. So we can see there the thickening of the arterial wall, and that when the hypertensive rats got lentils in their diet, that there was a slight reduction in that wall thickness. Okay, so we're actually changing the structure of the blood vessels, okay, and improving them in a positive direction. And lentils, specifically, we're doing that. And again, it's not linked to reducing cholesterol, because here you can see that all of the pulse diets lowered the blood cholesterol, but there's something about what was in the lentils is directly affecting the arterial wall. Okay. So since lentils were the positive pulse in that particular study, we wanted to go on and distinguish, okay, do green and red lentils do the same thing? So similar type study, this time we went longer for 8 weeks, and we also added an assessment that allows us to measure the functionality or the elasticity of the blood vessels. And that's what's being shown with this data and with these strain stress curves. And so I have some arrows that are going to come up here. So first of all, where the blue arrows are, so this is the normal blood pressure control rat. So you can see where the line is. With the SHR control, the hypertensive rat, you can see on the far graph how the line moves to the left. And when we gave the green lentils, you can see how the line moved back to the right. And what was really interesting, and we weren't expecting, is that this response here was as good as the WKY, and it was actually statistically lower. Okay, so we improved this back to normal. There was some improvement here with the red lentils, but you can see not nearly as much as with the green lentils. Okay. So this type of assessment and study allows us to show that lentils, particularly the green lentils, can also affect the vascular function. Okay. We've also gone on and done similar studies now looking at different types of beans. And so in this one, we were comparing black beans and navy beans. And so I've got here again marked the lines for the normotensive control, which is the WKY versus the SHR. And black beans, feeding them for 8 weeks, improved the vascular function. But the navy beans did not. Okay? And so again, this keeps coming back and making us think about seed coat color, obviously, is what we can see, the pigments that are present there, but what is that representing in terms of the different profiles of phytochemicals, flavonoids, and how can we go deeper with that to understand which of those compounds are the ones that are giving the protection to our blood vessels, or say even helping to reverse changes that are present. Another question that has come up with this work is, how long do you have to eat, say beans as an example, to see these effects on the blood vessels? And if you stop eating them, how long does it take for the effect to disappear? And this was done with the black bean study. So we had animals that we fed for the 8 weeks here. And then we had planned on both a 2-week and 4-week washout, where they were switched back to the pulse-free diet. And actually within the 2 weeks, the line had moved back to the left again. Okay, so it does say we need to have continuous consumption to maintain those effects, because there's perhaps very little storage in our body of what these protective compounds are. Okay. We're also interested in what are some of the molecular targets of the compounds that are in the lentils. And so this is just one example of a protein, phosphorylation of a particular protein that's been looked at, which from the literature was known to be elevated with hypertension there. And so you can see with each of the 3 diets containing the lentils that there was a reduction in the phosphorylation or activation of this protein compared to the control. Okay. I think something to think about from that previous graph is that also gives us a tool for being able to develop screening assays. Okay? It maybe doesn't need to be something based on Western blotting. It can be something else that we can do where we're making extracts, treating cells. And actually, we've done this more so in our work with buckwheat and testing out breeding lines to help inform the breeders which of the breeding lines show a greater capacity for affecting glucose uptake and potentially having anti-diabetes effects. Okay? And I think with so many of the other crops and agri-foods that we're working with, there's a lot more potential to do this, right? I mean, now we can do it looking at measuring certain chemical compounds, but we can also do it from a functional point of view and develop cell-based assays that could be high capacity and screen many samples at the same time. Okay. Another question that keeps coming up when we go to conferences and talk to people working on pulses is that right now the clinical studies and the evidence for the health benefits of pulses are based on conventionally prepared pulses. So overnight soaking and boiling, or perhaps studies might use commercially canned product. At the same time, we also know that the consumer wants ready-to-eat, convenient foods, and various approaches are being used through food processing to make pulses easier to use. So whether it's for at the distributor level or the consumer level, or what can we do with, say, pulse fractions. But as soon as we start changing what we're providing, we need to ensure that it's still maintaining the health benefits. Okay? So this is an example of one study that we've done to look at are there any effects of processing method on the health benefits of pulses using cholesterol lowering as the readout and the SHR rats, because as you can see, we could consistently across many studies see that pulses lower cholesterol. And what we did for this study is we compared overnight soaking and boiling. So this was with black beans. We had 2 types of milling, coarse and fine, for that treatment. And then for micronization, extrusion, and dehulling, those were all fine milled. And we just did this as representative of some of the processes that are being used. And we did find that the processing method is affecting the cholesterol lowering in this model. So the boiled and fine milled and extruded and fine milled had the least cholesterol lowering. Okay? And so the comparison here is to the pulse-free control group. Okay? So you can see a little bit of cholesterol lowering, not much. The boiled and coarse milled was an intermediate response, and the treatments for which the beans going into the diets had been micronized or dehulled retained the best cholesterol lowering in terms of magnitude. So amongst these different materials we prepared. We had the proximate analysis done. We know that the dietary fiber, soluble and insoluble, was fairly consistent across these products. We thought about resistant starch as a potential difference amongst these. And with respect to the dehulled, resistant starch probably is a major contributing factor to that cholesterol lowering that we saw on the previous graph. Okay? And so with these dehulled, we were feeding the cotyledon. So we had removed the seed coat. So in this case, we're not having, say, the presence of the phytochemicals in the seed coat being present. And so perhaps it was the combination of dehulling and we boiled that material led to the amount of resistant starch that we see here. The micronized sample was the other one that had the best cholesterol lowering, but you can see that it has kind of an intermediate level of resistant starch. So I think this is kind of just an opening kind of experiment showing us that, yes, as we develop food products and move forward, we need to be kind of working in concert to know that the food technology that's being applied is also resulting in maintaining those health benefits. And of course, we just did, one treatment for micronization, one for extrusion. So there's still much more to explore on how to maximize each of those different approaches. Okay, so now I'm going to do a little sum up here on pulses for your pulse. And recall that I've shown you, we started out with our first clinical study where we showed that giving MITS pulses could improve blood flow to the legs of people who have advanced cardiovascular disease. Then we went to our animal models and we're able to show that lentils, and particularly green lentils, are actually changing the structure and function of the blood vessels. And you know what? There's no other pharmaceutical out there that can do that, really change the structure in that way, right? So I think it's really exciting to see what food can do in this respect. But it's interesting, we talk to people about this and they say, oh yeah, that's really neat, but being able to move this on to the next step seems to be challenging. And to be able now to do some of the follow-up work and to say actually get a product or products in the market is where we need to go to really make this benefit the public. We also showed that black beans can improve the blood vessel function as well. I mean, there's going to be, in terms thinking of human studies in the future, right, we still have more to figure out, what's the dose, what's the frequency of consumption that is going to be important. And then as we develop new food products, we need to be thinking about how processing method, or at least testing, how is processing method, is it able to maintain what those health benefits are of the whole pulse? Okay, so now we're going to switch to part 2, fats for your fat. And much of this research has been framed around obesity. And I'm going to be focusing kind of on 3 themes with this part. So we've been looking at adipose tissue. Okay, so our fat cells or adipocytes that make up our fat tissue. And interspersed with our fat cells, we have immune cells. Okay, so that becomes important. Obesity increases the risk for atherosclerosis. So you're going to see there's a blood vessel theme here still. And also there's a liver theme or hepatic steatosis, because in obesity, as the subcutaneous and visceral fat stores get filled, the lipid that the body, or fat that the body needs to store, kind of spills over from those organs and has to go somewhere else to be stored. And so organs like the liver that typically don't store fat start to get higher levels of fat. Okay? And so actually hepatic steatosis, or non-alcoholic fatty liver disease, is becoming one of the major reasons for liver transplants. And unfortunately, that's expected to increase in the future. Okay. So much of our work has been around the omega-3 fatty acids, and particularly plant-based ALA, and how does it compare to EPA and DHA from fish oil. Omega-3 fatty acids, right, have a reputation of being anti-inflammatory. And questions that we're looking at now are to see, are there overlapping effects or, say, separate effects of ALA versus DHA, for example. Okay, and Harold Akama is up here in the audience too, and he's also been a major one posing this question about, you know, do we really know what these different omega-3s are doing, and is there something unique that ALA is doing? So with this work, we've been using a couple of different models, and one is to do diet-induced obesity. So this is where we feed rats a high-fat diet for, say, 12 weeks. We can buy strains of rats which are obese-prone and feed them the different oils that are down there in the corner. And I'm going to put up a fatty acid chart here, but it's just to make one point, and I just want you to focus in here on what's in the square, and that is by comparing high oleic canola oil, labeled the HC, conventional canola oil, or a blend of canola and flax oil, we could create a nice comparison here of ALA, right? So from 3 to 11 to 22. And we typically look at the fatty acid composition of different tissues, and in part to kind of address the questions we get about, well, does ALA how well does it really get converted to EPA and DHA? Okay, so you go to conferences where there's people who do a lot of work on fish oil, they're always challenging us, oh, well, you know, ALA isn't as good for doing that. I like to counter with what I see happening in tissues and in rats that have only been fed ALA. They've never been fed a DHA molecule. And yet we can see amongst these different groups that they're with the total, that the canola oil and CF, which is the canola flax oil blend, has an increase in total omega-3. Same with EPA. It looks like a larger increase there, but if you look at the scale, the amount of EPA is quite low, because most of what we've got in liver tissue, at least for DHA, or for omega-3, is largely DHA. Okay? And so you can see with the increasing amount of ALA that we have a bit higher of the DHA. But maybe the other way to look at this is they've all got pretty good DHA, except for the group that got the really high omega-6. Okay. When we look at what happens with the amount of fat in the liver, so this fatty liver, and percent lipid in the liver, we saw that the blend of canola and flaxseed oil was best for lowering the liver lipid. And it was equivalent to our weight match group, or this was the group that had the lower body weight. And so right now for humans who have this condition, losing weight is really the only effective method that there is for reducing fatty liver disease, because there aren't any pharmaceuticals for this. Okay. Okay. Then we went on to ask, okay, does it matter which of the omega-3s we give in terms of lowering the hepatic steatosis? So this time we switched to a genetic model of obesity. So you can see here the FAFA rat. So one of the advantages here then is we can feed a lower fat diet. And because of their genetic mutation, they get very fat. And we changed the type of omega-3 that's in the diet. And this time we purchased high purity EPA and DHA so that we could do this comparison. And it turns out that if we look at the percent lipid in the liver, that the DHA group here maintained a level of lipid in the liver that was the same as our baseline group. So we prevented any progression of the increase in liver lipid that you see in some of the other groups. And the EPA group did that to some extent as well. We can use liver sections from the animals to look at what the size of the lipid droplets are and characterize the size, and show quantitatively that the DHA group had a smaller average lipid droplet size. And then we do investigations to see if we can explain why is there less lipid in these livers. And so one of the questions is it because there's less synthesis? And in this particular study, we saw with the DHA group and also with EPA that there was lower levels of the enzyme fatty acid synthase, which is an enzyme which is synthesizing triglycerides or fat in our liver. So DHA was actually reducing the amount of synthesis and in that way contributing to the lower lipid levels. Okay. Improving the lipid levels, lowering them, can also help improve insulin sensitivity. And so in this graph, we have the lowering of fasting insulin. Okay. And so this is where we also have this connection between diabetes and obesity and fatty liver disease. Okay. So what happens in adipose tissue? And just want you to stop and think about adipose tissue is not static. It's very dynamic tissue because every day we're storing calories after we eat and we're pulling out calories from fat when we're in our fasting stage. So we've continually got energy moving in and out, and our fat cells are turning over all the time. It doesn't matter what age we are. We're generating new adipocytes, and there are other adipocytes in our adipose tissue that have gotten to the end of their lifespan. There's estimates maybe they have about a 7-year lifespan. So they're continually turning over. And so because of this turnover, I think we've gone another way through nutrition to affect what's happening in our adipose tissue. Also, what happens in obesity is that the size of the fat cells increases. We get more of these different types of immune cells, and then we get more pro-inflammatory molecules being produced. Okay? And so what we've been able to show by feeding a diet which is high in ALA from flaxseed oil, we can reduce the size here of the adipocytes. And if we reduce the size of the adipocytes, we can have less production of these pro-inflammatory markers. Okay, so I have a couple of examples here, TNF-alpha and MCP1. But what is really neat is that these changes are happening even though there was no reduction in body weight or in the adipose mass. So we can change the characteristics of that adipose tissue without reducing the amount. We can change the size of the cells, and we can change then what's being produced. And this has gotten to a concept which is in the literature about having healthier adipose tissue. Okay? And what are ways that we can achieve that? Okay. We also showed with this study that with the flaxseed oil, we can reduce, so where the green arrow is, T cells, which are a type of immune cell. Okay, so we're affecting not only the size of the fat cells, we're also reducing the immune cells that are present. Okay. Okay. So now I want to show you a couple of examples of some cell-based work that we've been doing. And up here I have work that Samantha Pauls has done. So she's a postdoc with 3 of us. So she has, I think, a challenging time that way. But she's been able to show in a cell model of these monocytes or macrophages that treating them with ALA can reduce these pro-inflammatory cytokines that are being produced. Okay. And then we've also gone on and looked at how these immune cells, so they're initially monocytes, and then when they move through the blood vessel wall, they become macrophages. And then if these macrophages start engulfing fat and LDL, they become foam cells and then plaque. And so if we want to stop things or slow things down at a very early stage, then we need to focus on this, the monocyte adhesion and transmigration. Okay? And so some of the work that Lisa Rodway has been doing is to look at adhesion of these monocytes to endothelial cells. Okay, so say here, these are the endothelial cells, these are the monocytes. So these get labeled with a fluorescent dye in green. And I know this isn't showing up here very well, but quantitating them, it was only with DHA that we saw a reduction in the adhesion of these cells. Okay, so now we're starting to build on this a bit more from a cell basis. But we've also decided to go a little bit wider with our exploration and use a microarray, a gene expression approach, to start thinking more broadly about what some of these targets might be for ALA and DHA when they are affecting the function of our immune cells. Okay. And so we've got lots of information back from this. And so all I'm showing here is the top 10 hits for upregulated transcripts. And so a list for ALA versus vehicle and DHA versus vehicle. And the ones in yellow are unique to either ALA or DHA. Okay, so kind of this question that we had initially, we're seeing that there are some unique hits with ALA and DHA and some overlapping ones. Okay, and so we're going to be working through this more. The PCR to confirm that these genes are actually changing with ALA is proving out, and one of the next steps is going to be see if this holds true in one of our current clinical studies. And so we have just finished the recruitment for our OxBio clinical trial. And so we've been running this trial, recruiting 24 women who have a BMI over 30, and they're doing a randomized crossover design where they're taking flax oil or flax oil capsules or DHA capsules for 4 weeks. And then we're measuring a variety of outputs here in terms of oxylipins, fatty acid, markers of inflammation, adipocyte function, immune cell function, and so forth. And so, again, this is a team grant that we have to look at this. And so this is kind of how we're extending the work, what we're finding out at the cell and animal level into humans. Okay? And so then to sum up fats for your fat, we're seeing that omega-3 fats can help reduce hepatic steatosis, promote a healthier adipose tissue. We think that there's some unique functions for ALA and DHA. And so now I'm going to put up a next slide for consideration. So this is just to get you thinking, and for me to think too, okay, so what does it mean with all this, like in terms of knowledge translation? You know, what does this mean for us in kind of our everyday basis? So I think I've shown several ways in which pulses are affecting blood vessel structure and function, right? All of us are aging, whether we like it or not. A part of aging is that we all develop atherosclerosis to some degree. So I think pulses are one of the tools that we have in the food box for helping our vessels. And when I look at how atherosclerotic disease is accelerated, what our risk factors are, obesity, diabetes, inflammation, these all seem to be things that the omega-3s may be helpful with. So in the end, I think I'm going to propose pulses for your pulse and fats for your fat. And oh yes, one more thing. We've got another study we're doing on pea protein. This may not apply to any of you, but I'd just like you to pass the message on if you know anybody that would like to participate in a clinical trial. This is a weight loss study in which we're comparing whey protein and pea protein and to see if they are equivalent for maintaining muscle mass and body composition. And if you know anybody that might be interested, you can, well, we have a study info email, but you can just put them in contact with me and I can put them in touch with our study staff. So, of course, lots of acknowledgements here. This doesn't happen without the funding, all of the people supporting this, my co-investigator, trainees, technicians, collaborators, study coordinators, facilities and so forth. So, there you go. And I'll leave you with Mr. Bean.
Thank you, Carla. I'll now open the floor up for questions, if there are questions from the audience. Hopefully you've been thinking about Dr. Taylor's challenge to you to think about the food system and how to incorporate some of the knowledge that you learned today into your own research and research thoughts. I might start the ball rolling. In some of the cooking methods that you used, you said you soaked and then you boiled. Did you leave the water with the beans?
No, we haven't because okay, so yes, I know there's phytochemicals being tossed out there. We've kind of approached it, that's kind of typically what consumers are doing now. So that's the approach we've taken there. But yes, you raise a point. What's being lost?
So I'm just wondering, should we advocate for different cooking methods for pulses, looking at keeping the water instead of throwing it away? If we're losing some of those active components.
Yeah, and I think it depends, right, on what your end usage is, whether having that water there works or not.
Yes, Nina.
I have a question. I don't know much about fats, so you talk about omega-3s, ALAs, and DHAs. Are omega-3s, AHA, or ALAs and DHAs, how are they different from each other?
Okay, so they differ in chain length. Okay, so ALA's 18 carbons, 3 double bonds, and of course it's an N3. And then we can elongate and desaturate. So we get to EPA and then DHA, which is 22 carbons, 6 double bonds, and also an N3.
And are they classed as omega? Are they all classed as omega-3s, or this is where I'm stuck on the omega-3?
Right. So if the bond at the methyl end, right, is 3 bonds in, all of those belong to the omega-3 family.
Okay.
Right.
This is where I had some confusion. Okay, thank you.
Right. So yeah, and then because usually, I mean, we're also comparing to those that are the omega-6, omega-9, and so forth.
I have another question.
Sure.
It's not clear to me. It was very clear in terms of the amount that you were feeding for the pulses, which was a reasonable amount. I wasn't sure about the oils because this is animals studies, but in terms of equivalencies, how much would a person have to consume to get the benefit? Does that make sense to you?
Okay, so with the animal studies, with what we're doing to, combine half and half flaxseed oil and say soybean oil or canola oil, right? I mean, that's not going to be a typical proportion that we have in our diet anyhow. So yeah, we're really increasing the amount that way. But say, I didn't talk about it today, but when we've done our human studies and say a study where we're introducing canola, well, we want to make sure there's either canola oil versus a Western mixture of oils. if we're providing people with a couple of food items per day, we were giving them about 25 grams of oil per day is the equivalent, whereas the total amount of fat in their diet might be around 60 to 70 grams. So in that case, we were trying to replace a third of it.
Okay, okay, thank you.
Yes, question here. Yes.
I was wondering, in the clinical study, how did the people who were receiving the pulses, how did that change their diet? Like, was it, were they eating the exact same things in addition to pulses, or was it replacing something else in their diet? Like something convenient that maybe wasn't as healthy, but now that they had convenient pulses?
So we gave them free choice as to what they were going to alter in their diet. And so some people would tell me, like if it was a day where our item we were providing was a soup, then they'd say, well, I then planned my lunch around that. Or if it was an entree we were giving them, they would kind of plan their other meal around that. But we did have, before they started the study, and a couple of times during the study, we had them fill out 3-day food recalls. And so we analyzed those. And so even though we left it up to them, at the end of the study, they weren't different in terms of what their total energy intake was or the macronutrients. But those that were consuming the pulses, we could see a slight increase in their folate, for example. And pulses are a good source of folate. But this is the type of study where we're seeing, if we just give them something, let them decide what they're going to replace, can we see an effect? And we did.
Adam?
Sure. Was there anything else different about the two lentils between the red and the green? Maybe you thought about that might be affecting the outcome?
So in terms of, you mean composition or?
Maybe one. So the two were matched for total pulse amount, right? So it was fed, a rat was fed, or who was fed X grams of red lentil, and then the same was for green lentil. But if you're just matching for total pulse, then other things change, like protein content, total fiber content.
Oh, okay, yeah. Actually, we did do proximate analysis, and so we did adjust our semi-purified diets for the rats based on what that proximate analysis was. So we did that for the macronutrients, but we found once we got into multiple diets that we were comparing, we had to make a decision, were we going to keep the fiber just what was coming from the pulses, right? Versus trying, to equalize it with some cellulose, which is typically in there or not. And so we decided just to leave it as the fiber that was part of the pulses, because when we put in 30% by weight of the pulses, we're getting an amount of fiber that's equivalent to the control diet where fiber is coming from cellulose. So I mean, it's a different type.
May I ask a follow-up question?
We've got limited time, so I'm going to move to Gerardo. You can ask afterwards. Gerardo?
Thank you for your presentation. I just have a question about the study that you did with the Papa rat. That's a common model used on metabolic syndrome as well.
Yeah.
Did you look into other markers such as blood pressure or triglycerides, cholesterol in that model used in that diet? Did you see any difference when you looked into it?
Okay. So recall, many of these studies we've looked at blood pressure, and although maybe not so much in those early lipid studies, I don't recall changes in cholesterol. Sometimes we have changes in circulating triglycerides often, right? Because these animals already have elevated levels, right? Triglycerides, insulin, and so forth. But yeah, we haven't focused as much on those lipid markers in blood as opposed to more understanding the lipid metabolism in the tissue.
Harry?
That was a lot to digest. So following up on Adam's question, red and green lentils, these rats were fed cooked lentils, right?
Yep.
And you threw away the water
Yep.
after cooking. Don't red and green lentils, don't they have very different textures and cooked quite differently? So I'm curious, did you measure like total phenolic content to see if that was the indicator related to why? It's not the color, it's something else.
Could be something else. Yeah, I know. I agree. We don't know what it is, and but I guess coming back to your question about the preparation. So, for green and red lentils, we cook them as a consumer, each to their appropriate doneness. And yes, we did discard the water. Then each of those were freeze-dried and powdered. And so it was an equal amount of powder that was put into each of the diets on a weight basis. But yes, because of the different size of each of those lentils, right, they're going to be representing a different amount of, lentils in that way. But I guess at this point, we've been going more for the biological effects. And I think now it's time to do more of that characterization. What's in what we're feeding, and what is showing up is actually absorbed, bioavailable in the animal. And also these days, how is the gut microbiome handling some of that material too, and changing those potential phenolics which are actually getting absorbed into the animal too. So just having a measure of what it is in the starting material, there's still a lot of different steps that happen to it.
Are you sure? Okay. Yes, we'll leave our final question to the front row.
Still wondering, it wasn't straight flax oil they were being fed, was it flax and canola together, or just?
So the last study I showed, it was a combination of flaxseed oil and soybean oil, because the typical rodent diet is based on soybean oil. So we just did those two. But those are mixed into like a semi-purified diet where we have like cornstarch is the carbohydrate, casein for protein, and so forth. So they get all those components together, not just oil by itself.
Okay, I think for the sake of time, we're going to wrap up our questions here. Please join me in thanking Dr. Taylor for